Welcome to the OpenQuake series of online workshops sponsored by the United States Agency for International Development, USAID, as part of the TREC project. In this video, we will talk about the theoretical framework required to understand and model probabilistic seismic risk in the OpenQuake engine. We will first review the concepts that we have covered so far in previous sessions, since they are the foundation of the probabilistic seismic risk. We recommend that you become familiar with the previous videos of this series, earthquake scenarios, and probabilistic seismic hazard assessment to be precise. You can find the link to the videos in the video description right below. We will then continue talking about the different OpenQuake calculators for probabilistic risk. So the type of results that we can estimate with these calculators and what is their applicability. Then we will move on to have a hands-on example for Quito. This will be done in a different video session. But in that video session, we will see how to prepare the input files, how to estimate economic and human casualties using the OpenQuake engine, and how to visualize the results in QGIS using the QGIS plugin, as we have seen in previous sessions. So let's refresh some of the concepts that we have seen in previous sessions. By now, you should be fairly familiar with the concept of seismic hazard and seismic risk. So what is the difference between seismic hazard and seismic risk? We said previously that hazard refers to the existence of one or more sources of seismicity that can generate earthquakes and the subsequent effects of these seismic events at the level of the ground. The exposure is the man-made environment that we have built and that is exposed to those sources of seismicity and to that seismic hazard. And the vulnerability is the inherent condition of these exposed elements to the effects of earthquakes and their likelihood of suffer damaging or loss. Risk is the result of having these three in a temporal overlap in space and time. So in Module 1, we mentioned the different OpenQuake calculators to estimate hazard and risk. Module 2 focused on the calculators for the earthquake scenarios, while Module 3 focused on the classical PSHA calculator, covering the hazard component. In today's session, we are going to concentrate on the event-based risk and damage calculators. This is the calculator used to generate the global risk map of the GEM Foundation and all the risk country profiles that are available in the GEM website. We are providing a link to all those websites and all that information in the video description as well. So the earthquake scenario calculator. When modeling an earthquake scenario, we have a deterministic event for which we can define the magnitude, the location, and the characteristics of the earthquake rupture. On the hazard component, we can estimate the ground motion fields by specifying one or more ground motion models or ground motion model prediction equations and the local side effects. So we saw previously that in OpenQuake, we can specify uniform soil properties. We can also specify BS30 values, and even now we have the capacity to provide the engine with amplification functions. So in this way, we can estimate the median ground motion field, or we can simulate multiple ground motion fields to take into account the aleatory or random variability of the ground motion model or GMPE. The ground motion fields indicate the level of shaking intensity in the study area, in the area that we have delimited, where we're interested about the ground shaking intensity. If the purpose of our assessment is to evaluate the impact of the shaking on the built environment, that is seismic risk, then we need to add additional information. We require additional input files. So an exposure model that features the geographical location of the physical environment and its inhabitants, the population, namely our assets, and we also have the corresponding characteristics, as we have seen previously, their physical characterization through a taxonomy or a building class. For example, one-story wooden houses, three-story masonry buildings. If we also have the replacement costs, the number of occupants in those assets, and any other additional attributes that we have seen before we added as stats in the exposure model, that can contribute to the understanding of the exposure. So all of this is what we call the exposure model, and this exposure model describes our built environment. Then we would additionally have to input fragility and vulnerability curves, and which are models that allow us to correlate the level of ground shaking intensity with the probability of exceeding a certain damage state, as we have seen before in the case of fragility, or reaching a certain loss ratio in the case of vulnerability, for each of the building classes that we have in the exposure model. So we have also seen that loss ratios represent the loss as a proportion of the exposed value, which could be, for example, the replacement cost of the economic cost of a building structure, but it can also represent the loss of the occupants in that structure. If preferred, rather than inputting vulnerability curves, the user can also input fragility curves in combination with a consequence model, and then you will be able to estimate damage and also economic and human losses. With all this information, we will be ready to basically estimate everything required for an earthquake scenario. So OpenQuake uses ground motion fields, the exposure model and the vulnerability model for each building class that we indicated or identified in the exposure model to estimate loss statistics per building class, per region, considering different components of the building stock, for example, structural or non-structural components, contents, business interruption. And we can also compute loss maps showing the spatial distribution of the losses across the region of interest. The ground motion fields can be generated from a finite rupture, as we have done in previous exercises, or OpenQuake can use actually pre-computed ground motion fields, such as the USGS shake maps. If the interest of the user is in estimating damage, then the scenario damage calculator uses a fragility model instead of a vulnerability model. The results in this case will be the damage distribution statistics for each of the assets. For example, what damage statistics we get, number of structures in its life, moderate, extensive, or complete damage states, the aggregated damage distribution statistic per building class or per region. And we can also see the spatial disaggregation of the damage into what will be actually like what we call damage maps. And with this calculator, if a consequence model is also provided as an input, in addition to the fragility, then the calculator is able to estimate consequences, and that is losses based on the calculated damage distribution. So in this way, it will be possible to estimate not just the not just the damage distribution and the spatial distribution of that damage, but also the loss statistics and the spatial distribution of those losses. There are other types of consequences supported by these calculators, such as injuries, fatalities, disruption time, repair time, and business interruption. So previously, we have seen hands-on exercises for earthquake scenarios, and these are available in the material for Module 2, which is available through these YouTube playlists and also in our training website. So now let's move on to see the probabilistic calculators. In probabilistic seismic hazard assessment, or PSHA, instead of considering a deterministic rupture, we want to consider all possible ruptures that occur in the region of interest. The OpenQuake classical PSHA calculator requires one or more source models describing the activity rate of all the seismic sources in the study area, their locations, and one more ground motion model or prediction equation, GMP, per tectonic region type. The epistemic uncertainty in both cases must be properly defined by logic trees. The user can include site conditions to take into account the amplification of the ground motion model in different soils. So this calculator follows the methodology originally proposed by Cornell et al. and in which the total probability theorem is used to estimate the probability of exceeding a set of intensity measure levels. The results are, as we have seen previously, seismic hazard curves, seismic hazard maps, uniform hazard spectra, and with this calculator, we can even do disaggregation of the seismic hazard. PSHA is the type of analysis that is used to generate seismic hazard maps that we see in the national codes or in the construction normatives and regulations that we can find for countries. So we have also done a hands-on example for classical PSHA that is available in the material for module 3 in our training website. So let's take a look now at probabilistic risk and some basic concepts of probabilistic risk. So to estimate probabilistic seismic risk, we need to have a seismic hazard model for which we can obtain the location and the activity rate of all seismic sources. For example, here we are seeing the geometry and the location of all the seismic sources in the region of Colombia. The hazard model includes active shallow faults, it includes area sources, it includes subduction sources, and even sources of distributed seismicity. Now we know that the activity rate of each of these sources can be represented by what we call the magnitude frequency distribution. So using all of this information that is available to us through the hazard model, the OpenQuake event-based PSHA calculator simulates the seismicity of a region for a given investigation time. That means that for each seismic source found in the source model, OpenQuake samples the ruptures that can be generated within this specified time interval. And so here's an example of the stochastic earthquake catalog for Colombia that is generated with this approach. This map shows the simulated seismicity for each year in a 1,000 years period with the geometry, the source type, and the location of each of the sample ruptures. This catalog can be used to identify which events may be of particular importance due to their frequency with which they are sampled from the model, from the magnitude frequency distribution, let's say, their importance due to their magnitude, their tectonic region type, and of course the location relative to our built environment, relative to the populated areas in the country. So as we know, if we have the characteristics of the ruptures, then for each sample rupture, we can estimate a ground motion field using the same approach that we have been doing before. Therefore, we have a set of ground motion models. With these ground motion models, we pass from those ruptures to ground motion fields. And the results of these ground motion fields incorporate the epistemic uncertainty and aleatory variability that is associated in the whole hazard model and that is described in our logic tree. So the event-based PSHA calculator uses the exact same input files that the classical PSHA calculator uses. The outputs of this calculator are very similar to the outputs of the classical PSHA calculator. So namely, we can obtain hazard curves, we can obtain hazard maps, and we can obtain also uniform hazard spectra. The difference here is that we will be able also to obtain as an output an stochastic event set catalog or an stochastic catalog. So what is this? These event sets are simulations of the seismic activity that has occurred within the time window of our investigation. So each event in the stochastic event set is completely defined by location, by magnitude, by depth, and by rupture geometry. So for each one of those, we can generate ground motion fields as we have previously seen. So this is the extra output that we will obtain from the event-based PSHA calculator. So when in addition to the seismic hazard, we also have information about the exposed elements, their physical vulnerability as well, it is possible then to estimate damage and losses using the OpenQuake engine, because these are the same models that we have been using for the earthquake scenario calculations. So an exposure model that describes our built environment, and a set of functions that describe how fragile or vulnerable it is, this environment is to the ground shaking. So now we have the required input models to estimate seismic risk. In probabilistic risk assessment, we want to, in probabilistic seismic risk assessment, we want to answer questions such as these ones. So basically, we would be asking what is the expected impact in a given region? And when I say impact, we mean actually damage and losses, considering all possible events that could cause significant ground shaking. So the question here is deeper. It's not just we have a single deterministic scenario. So it is considering all possible or significant events that can cause a significant ground shaking or damaging ground shaking in our built environment. The other key question is how frequently these events can occur in my region of interest. Is society prepared for these damaging events or this damaging event? Given what we know about the built environment, about who lives there, about how intense the ground shaking can be there, how vulnerable that built environment is. Also, which regions, and here we are thinking if it's a country, which provinces, which counties, if we're thinking about cities, which neighborhoods will be most affected by the earthquakes. So, in other words, which parts of society will be more affected by the earthquakes? Do we have enough economic, physical, and human resources to cope with this emergency, with those consequences, with that impact? How long will the region take to recover and rebuild the damaged infrastructure? And how long will our services, will our businesses be closed? And how long will the city or the country, how long will it take to recover and rebuild what was lost due to the event? So risk assessment through an event-based approach tries to answer all of these key questions, and it does it through a large considering the large uncertainties that we have in our models, and we have to understand also what are the main assumptions that are involved in the process. So how does it work? And here is the main example. Let's imagine we want to investigate the risk within a given time span, let's say 1 year. We can produce a representation of the seismicity in 1 year, a so-called stochastic event set for that 1 year. And then we can repeat that simulation of seismicity 10,000 times. And this will lead us to a total stochastic catalog representing 10,000 years of seismicity. So using the hazard model, the OpenQuake will randomly sample all possible events that will occur within that period of time. So for the first year, when we start this analysis, when our clock starts, an event, and let's call it event number 1, is sampled, okay? And it's an event with a magnitude 5.1 from an active shallow tectonic region type right here in this region of Colombia. We can see that it's occurring in the northeast. And because we have that event, its geometry, its magnitude, its depth, we have the rupture fully described or fully defined, OpenQuake will simulate the ground motion field sampling the aleatory variability. And we can see right here how the ground motion field looks like because we have in the source, in the hazard model, we also have available ground motion models. So we can estimate the ground motion field. So let's assume that at this location, in this particular point right here, according to that ground motion field, that rupture generates a PGA of 0.3 g. So this is the acceleration that is experienced given the distance of this particular point to the simulated rupture to our seismic source. And let's also assume that this already includes the site conditions, so the local quality of our soil. Let's also assume that in that particular point, in that particular location, our exposure model is telling us that there is one asset there. There is something exposed there, and this will be a single building. And our exposure model provides the physical characteristics of that building. So what OpenQuake will understand as the building class described in this taxonomy attribute. So in this example, what is there? What is in that particular point? In this example, we have a 5-story reinforced concrete building with a moment infill frames, building 2010. So we can also have information regarding the replacement cost as well. So how much this building costs and how many people are living in this particular building. And also, because we have a vulnerability model, we have a curve associated with this specific building class. And thanks to this curve, we can associate any level of ground shaking to a loss ratio, right? So basically, for this acceleration of 0.3G, for this particular building, where we have the information to understand from here in the bottom axis, understand what kind of intensity that is. And we will also be able to, thanks to the vulnerability curve, to understand what is the loss ratio or the percentage of losses, economic losses and human losses in this particular building. So once that is done, for this particular building, we know that in this particular year, for this particular event occurring in this particular tectonic region, given that location, that magnitude, and given what we have exposed in this site, we have a certain loss. And then if we take all the losses, if we repeat the exercise, not just for this point, but for all the points in this map, where we have exposed buildings, where we have exposed people, if we have the information about what we have exposed and the vulnerability, then we will be able to estimate the losses, economic losses and the human losses for every single exposed asset. And if we sum all of that, we will get to this result. So we will understand what are the aggregated losses from this 5.1 magnitude event. In this particular case, we are saying that for this event, the total economic loss is $12 million. And this event is causing 3 fatalities. But this is just one event in our stochastic event set. Once we are done doing that calculations, once the engine calculator is done doing this first event, it will sample another event. So it comes another event during that investigation time. We are going to call this event number 2. And this event number 2 has a magnitude of 6.1, and it's actually occurring at the other side of the country. It's in the subduction zone in the Pacific coast. And this time is affecting mostly the southeast of the country. And following the same procedure that I just described before, we have the ground motion field, we have what is exposed, we calculate the loss ratios not just for one site, but for all the sites, and we understand how much economic losses and fatalities are. We aggregate all of that, and then we obtain the losses for the second event. In this case, we're saying that this event is causing $57 million and 6 fatalities. And so our clock keeps going. We keep sampling events during our investigation time, and we continue evaluating the losses from each one of those events. For each one of those events, we have ruptures. For each one of those events, we have ground motion models, so we can estimate ground motion fields. And from those fields, loss ratios, and from those loss ratios, all the consequences. So if we keep doing that, we feel all this stable. We feel we understand for each one of the sampled ruptures, for each one of those events, what are the aggregated losses in terms of economic loss and in terms of fatalities. And this results in what we call the event loss table. So the event loss table describes the total economic loss across all our assets in the exposure model for each one of the seismic events. Now let's take a closer look at the information that the event loss table is providing us. Okay. So first, it's important to note that as indicated in the frequency magnitude distribution that we are using from our hazard model, clearly low magnitude events are sampled more frequently than high magnitude events. And this is because our magnitude frequency distributions in the source model are telling us that it should be so. Second thing that is important to notice from this table is that events do not occur in a particular order. They are randomly generated. So we're sampling randomly, always following the magnitude frequency distribution. Three, and also quite important, the largest magnitude event might not be the event that causes the largest losses, that causes the largest consequences, impact, economic losses, fatalities. And here we're giving this example. With the event with the largest losses, according to this table, is occurring in the year 6543. And this is a magnitude 5.9 earthquake in the active tectonic regime with a certain depth. It's quite a shallow earthquake, but this one is causing the most losses from all our investigation time, even though it's a 6.9 magnitude event and not, for example, an 8.1 subduction interface event. So it's very important to understand that the most damaging event not necessarily is going to be the one with the highest magnitude. Why? Because this is a table that is displaying risk. And remember that risk is the overlap of three things, not just the hazard, not just the magnitude of that event, but also what was exposed to that event and how vulnerable it is. So this is the value of having all those events here in a single table. And finally, also important to say is that the event loss table will only report events that were capable of generating a minimum loss threshold. So for example, for instance, an event of magnitude 7 in the subduction zone in the Pacific coast that, let's say, occurs at a 100-kilometer depth. So let's say an event occurring something around here, but let's say it's occurring like it's a very, very deep event, 100 kilometers, 150 kilometers, might generate a very low ground motion in the surface. And hence, it will not generate damage, and hence, it will not appear here in our table because it did not generate any consequences. So in the table, only events that cost certain minimum loss will appear in our table. So in risk assessment, now that we have this event loss table, in risk assessment, we also want to understand what is the frequency of the damaging event. So we already said this is the most damaging event, but we would like to understand, is this very likely? How likely is that we will see this within our lifetime, within the lifetime of the city's urban planning, within the lifetime of the buildings in the city, of the constructions that we're building right now, or the constructions that have been built within certain periods. So what is the likelihood that we will see this event and any other event in this loss table for that matter? So in other words, what we're saying is that we want to understand what is the return period, or seen from another way, the annual probability of exceedance of each one of the losses that we see here in the table. So how do we do that? To associate each event in the event loss table with a corresponding return period, we are going to do the following. Number one, we are going to sort the events in the event loss table from the highest loss value of interest. And here, let's say, I think we're sorting it by the fatalities, let's say. So we sort from the highest loss value to the least loss value. Okay, so we have it sorted. We are basically rearranging our table. And so what we are going to see is that the top loss right here will have 0 exceedances. Okay, the top loss was observed only once in my entire investigation time, and it has 0 exceedances. Okay, the next loss, this loss right here, has been observed once in my investigation time, and it has been exceeded once by the highest event recorded, by the highest loss recorded, and so on and so on. We see, we understand that for each loss, how many times it has been observed and how many times it has been exceeded. So what we are going to do is we're going to add an additional column to our event loss table with exactly that. We are going to assign a rank with how many times we have observed this particular loss. And then we are going to rate the exceedance of each loss, which is basically calculated by dividing the number of exceedances of that loss by the number of stochastic event sets. So in our case, we were saying that our event, our set, our stochastic event set is of 10,000 years. So what we're going to say then is that to understand the exceedance loss ratio, we're going to divide those numbers of exceedances by 10,000. So basically, we understand that we observed this only once in our entire period of investigation. So it has a rank of 1, and the rate of exceedance is only once every 10,000 or 1 over 10,000. That is what we call the annual rate of exceedance. And we can estimate the annual rate of exceedance for every single event that is in the event loss table. And interestingly, we can also ask the inverse question, or we can obtain the inverse of the rate of exceedance. So instead of how many times we're observing these every year, we can ask how many years it takes to observe this loss at least once. And for the first one, it's quite clear. If we have an stochastic event set of 10,000 years, then it took 10,000 years to observe my maximum loss, the highest loss that is on the table. And we do the same. We do the inverse. How many years it took to observe the second highest loss, and the third, and so on, and so on, and so on, until I have all the return periods. So we pass from having these randomly generated events to understanding which is the most damaging one, which one creates the highest losses. And we also pass from having them disordered to order them from highest to low, to understanding how many times we observe them within our investigation time. And hence we can we have now moved on to understand how frequent they appear in my investigation time. So as a result, we have this aggregated loss table now sorted with the rate of annual rate of exceedance for every loss observed, and with the return period of every loss observed. So now we can plot those expected losses. So basically my aggregated losses, I have my economic losses right here, and I have my human losses right here, and I can make a plot of my losses versus how frequent they are. So I can plot my losses versus their annual rate of exceedance, or I can plot my losses versus their return period. And this is how we obtain this graphic. This is what we call a loss exceedance curve, or an aggregate loss curve. So loss exceedance curves, also called exceedance probability curves or probable maximum loss curves, they present all the estimated losses for each event in the stochastic event set. And since we have sorted them, they are sorted according to their annual frequency or probability of exceedance, or they are sorted corresponding to the return period. So we see how in this particular graph right here, we can see how the uncertainties can be propagated into our loss curve. So for every line that you're seeing here in this particular loss curve, each one of those lines represents a realization of the risk model. So basically each branch logic. Each branch of our logic tree is a realization of risk, and each one of those is going to have its associated loss table, and then each one of those, if we plot each one of those losses against their return periods, then we're going to have basically a curve that looks like this, that is telling us what is the return period in years for each one of the losses that I observed in my investigation time. And I can see basically the range of uncertainties that is translating into my losses, into my risk assessment, let's say. So loss exceedance curves are very useful. They are used to inform risk management decisions. So for example, for risk financial transfer and for insurance policies, these curves inform about the appropriate level of catastrophe risk coverage that a certain insurance policy should provide. So, for example, before choosing the level of insurance coverage, governments can decide if they would they prefer to be insured for example, very frequent losses that can come but are low in impact, right? Or if they have enough cash in the bank to be prepared for response, emergency response for those very frequent but very low impact events, and hence they might decide to better be insured against the higher um, impact events that are less frequent, but due to their higher impact, they do not have the level of cash in their bank, or in they do not have the level of economic resources to respond to those higher events. And so there can be a threshold for which, for the higher events, we would choose a certain insurance policy, and that insurance policy can cover us up to a certain a degree if we understand for which kind of events we want to be prepared. So extremely rare events or less rare events that can occur. All of that is the process, it becomes the process of decision making in risk assessment. So it is also possible to estimate risk metrics per asset. Why? Because while we were doing this particular process of generating the entire stochastic set and estimating the losses, we said that we had the aggregate loss table because we were summing the losses of each individual asset, right? But if we keep a record of the losses of each individual asset as well, then we can also estimate the risk per asset, right? So in this case, we can have something kind of a table for every asset losses generated by each event, and we can also compute the same statistics. So we can compute, for example, median statistics, quantiles of the risk of each one of the assets. So using the average risk matrix of every asset, it is possible to visualize the distribution of the impact in, let's say, economic losses through average annual loss maps. And what I am showing here is an average annual loss map coming from the event-based analysis that we just did for Colombia. So in this case, what we're looking is at the average losses per each region, per each administrative region for Colombia. So basically what we're doing is we have all the losses that occur during the investigation time for each one of those regions, for each one of the assets inside of those regions. We can aggregate those losses and show them and show that average per region. So basically what we're showing here is the average annual loss maps. So this map indicates the range of absolute economic losses that each municipality has experienced on average per year through that investigation time. So basically what we're seeing is that the map ranges in different colors of red, and each one, each region has a certain color. Obviously, the ones with the highest reds are the regions that during this investigation time that we were doing, if we take all the losses that these particular regions suffered and we divide them by the investigation time, basically we're analyzing them, we can see which ones lost, which ones have the highest economic losses in this case. And in this type of maps, it's quite usual to see reds in regions where most economic assets are located, where most productive assets are located, where most people live. Why? Because it's regions that have high exposure, and hence, through the whole seismicity that we have simulated, they tend to accumulate or accrue more losses because basically because they concentrate most of what is exposed. They concentrate our built environment. And that's why, for example, for Colombia, we can see clearly that Bogota lights up right here. We also have other big cities lighted up. Medellin, for example, where we have been simulating or making some simulations of scenarios previously. Cali, which is, for example, a city that is close to a high hazard zone, and it concentrates a lot of people. You can see that this region um, tends to appear in red, or with a high level of loss because they concentrate a lot of people. Um, but we can do something else. For example, what happens if we take that average annual loss of each one of those regions, but we divide that loss by what is exposed in each region? So basically, what we're asking ourselves is, we want to see which of the regions, through the whole seismicity that we just modeled, lost more of its value given the seismicity that we simulated. And hence, in this type of maths, where we're actually representing average annual loss ratios, because remember, we're taking the losses and dividing it by what's exposed per region, we see a little bit different of a map, because now we're not seeing highlighted where most people live, where most productive assets are. We see highlighted the regions that lose more of their economic value, of their inhabitants, through the simulated seismicity, because they have certain inherent conditions that make them lose more. So it could be their physical vulnerability, it could be their proximity to more to zones of with higher rates of seismicity. It can be their site conditions that they're on that can potentially amplify the effects of the earthquakes, and hence become more damaging, etc., etc. So these maps, this type of maps helps us to identify which are the most vulnerable parts of society to earthquakes, given their inherent conditions that we have explored through the whole process of risk assessment. So those physical characteristics, that seismic hazard, etc., etc. So let's summarize then the input and output files for the OpenQuake probabilistic event-based risk calculator. So this calculator uses as input files the stochastic event sets or stochastic catalogs that we just discussed, an exposure model, a built environment, and a vulnerability model for each loss type. So using an event-based Monte Carlo simulation approach, it is possible to estimate the loss distribution for individual assets, aggregated loss distributions for a particular distributed portfolio of assets within a specified time period, and obviously as well loss maps. We will also, or we can also obtain, as we have seen, our event aggregated loss tables. So basically we have these big tables where for each event we have all the aggregated losses from every possible scenario that we sampled in our investigation time. So all of this can be produced with this calculator. Again, if instead of a vulnerability model, we're providing the calculator with a fragility model, then we will be using the probabilistic event-based damage and consequence calculators. And in that case, the same. We can obtain the same types of outputs. So obviously our risk curves, aggregated losses, and understanding how frequent they are, the aggregated risk, prevailing class, spatial disaggregation of the losses, and the event loss table. But because we're providing a consequence model, then we would also be able to obtain damage metrics as well. So very important, just to some final remarks about this. Why is event-based approach important in portfolio risk assessment? So Point number one, classical PSHA evaluates the hazard integral at each site in an independent way, independently. But portfolios are spatially distributed across a region, and during a given earthquake event, many assets are simultaneously impacted. If that earthquake has a higher average event term, due, for example, to an increased stress drop, then all of the buildings will experience higher than average ground motion. This correlation in the response of the buildings is further attenuated by the fact that closely spaced assets are likely to experience similar levels of ground shaking. So what we call the spatial correlation of the intensity for a given rupture event. And then by generating each stochastic event set separately, we're estimating the correlated ground motion fields and then calculated the damaging and the damage and the losses, all those consequences across all assets for a single correlated ground motion field. So this is repeated until for a large number of times to ensure that we're also covering rare events with low probabilities of occurrence. Just to finalize, also remember that you can find very useful information about the OpenQuake software and complementary tools from the GEM Foundation in any of those links, in any of these links that I'm showing right here. So remember, you have the availability of the global risk and hazard maps in the global earthquake model site. We also have the engine, obviously the engine repos where we maintain the engine, the OpenQuake documentation, so the risk and hazard manuals, testing, additional tools, etc. We also have the platform where you can find fragility models, researchers sharing their knowledge through the platform. We also have the country risk profiles, the OpenQuake platform again, and also we have this YouTube website where we will be uploading training sessions, hands-on exercise, etc., that you can refer to in the future. So thank you very much for visiting, for seeing the video. Like it, subscribe to our channel if you want to be updated about upcoming events, about new videos, about new training material. Like and subscribe, and also follow us on our social media. We are in Twitter and Facebook and in Instagram. So thank you very much, and see you soon, hopefully.